Hi everyone, my name is Mahdi Kazemi and today I'm presenting my work titled ForeSI Success-Aware Visual Navigation Agent. This is a collaboration with my great collaborators at the Australian Institute for Machine Learning, the University of Adelaide, shown here. The task that we are interested in here is object called visual navigation, where the agent is placed in a 3D environment and using visual observations, here RGB only, is tasked to find the closest instance of a given target object. Most of the state-of-the-art methods here to really fail to identify the target object because they simply do not learn a good representation of that target object. And what we are trying to do in order to address that here is to enable the agent with an imagination of a representation of a state, which we call subgoal state. And that subgoal state could be a very close state to the final target object, where the object is visible, or the goal state, the exact final state itself. In order to achieve this, we develop a framework which has three main components. The first component is to enable the agent with learning how to identify those subgoal states. Now this happens in hindsight. After the episode is ended, the agent looks back and identifies the subgoal state that was optimal in order to be generated next time in the beginning of the episode and then navigate towards it. The next step, or the next main component, is then learning how to generate those subgoal states during test time, which happens in ForeSI in the beginning of each episode. And then the final important component of our framework is how to integrate those with actor-critic reinforcement learning in an efficient way that improves the performance. So in order to understand how this works, we need to have a quick look at the overall objective of actor-critic, specifically A3C that we are using here. So we have two different objectives. One is for the policy, the other one is for the critic, or the value head, which estimates the total return of an episode from every state. Now that value is then used to train a better policy using advantage function, which is the immediate reward at each time step plus the discounted temporal difference of the estimated values. What we change here is that we change the essentially the observed state by the value function, or the critic, and we change it to a weighted average of all the states that have been observed so far in an episode. And the weightage of each state is then calculated using multi-head attention mechanism. And then what is important here is that we use those attention weights essentially in order to identify the subgoal state that is important for us, and we pick the augmax, the state with maximum attention value. So we can have a look at the overall algorithm of training one single agent of ours, which we call ForeSI. And essentially in this algorithm, we alternate between training the original RL objectives and the ForeSI. So ForeSI, like after training the original normal RL algorithm and sampling the actions from the policy, then we start collecting trajectories or states and the weightages that we observed how to identify, and we collect them in a replay buffer that we introduce here. And that replay buffer is filled with these subgoal states, and then we train, if the size of that replay buffer is big enough, we train our imagination module, or the ForeSI subgoal generator. We also add this extra exploration mechanism with extra noise in order to make sure that our agent doesn't get stuck predicting or generating the same goal. In order to test our method, we use AI2Thor, commonly used benchmark with discrete actions. Essentially, the agent can rotate, forward, tilt, and stop. And we have two different setups of the environment, setups of the environment, in order to effectively test different aspects of our method. And in terms of robustness and success rate, we can observe that our method added to different baselines, it can improve the success rate by 3 to 5% absolute improvement. And in terms of efficiency, it can improve the method even in the presence of an off-the-shelf object detector. It can improve by 2 to 3% of SPA. We can qualitatively check two different trajectories of a baseline method, whereas our method in basically an episode, which is the agent is trying to find a box, which we can see here on the left hand side, the baseline fails, even though the box is observable at some point or in some of the states, whereas our method can directly navigate towards that. Thank you very much for your attention. Please check more details in our poster and the paper, and feel free to reach out if you have any questions.